Organic chemistry is a chemistry subdiscipline involving the scientific study of the structure, properties, and reactions of organic compounds and organic materials, i.e., matter in its various forms that contain carbon atoms. Study of structure includes many physical and chemical methods to determine the chemical composition and the chemical constitution of organic compounds and materials. Study of properties includes both physical properties and chemical properties, and uses similar methods as well as methods to evaluate chemical reactivity, with the aim to understand the behavior of the organic matter in its pure form, but also in solutions, mixtures, and fabricated forms. The study of organic reactions includes probing their scope through use in preparation of target compounds by chemical synthesis, as well as the focused study of the reactivities of individual organic molecules, both in the laboratory and via theoretical study. The range of chemicals studied in organic chemistry include hydrocarbons, as well as myriad compositions based always on carbon, but also containing other elements, especially oxygen, nitrogen, sulfur, phosphorus and the radiostable elements of the halogens. In the modern era, the range extends further into the periodic table, with main group elements, including Group 1 and 2 organometallic compounds, i.e., involving alkali or alkaline earth metals, metalloids or other metals. In addition, much modern research focuses on organic chemistry involving further organometallics, including the lanthanides, but especially the transition metals. Finally, organic compounds form the basis of all earthly life and constitute a significant part of human endeavors in chemistry. The bonding patterns open to carbon, with its valence of 4, formal single, double, and triple bonds, as well as various structures with delocalized electrons, make the array of organic compounds structurally diverse, and their range of applications enormous. They either form the basis of, or are important constituents of, many commercial products including pharmaceuticals, petrochemicals and products made from them, plastics, fuels and explosives, etc. As indicated, the study of organic chemistry overlaps with organometallic chemistry and biochemistry, but also with medicinal chemistry, polymer chemistry, as well as many aspects of materials science. History. Before the 19th century, chemists generally believed that compounds obtained from living organisms were endowed with a vital force that distinguished them from inorganic compounds. According to the concept of isolism, organic matter was endowed with a vital force. During the first half of the 19th century, some of the first systematic studies of organic compounds were reported. Around 1816, Michel Chevreul started a study of soaps made from various fats and alkalis. He separated the different acids that, in combination with the alkali, produced the soap. Since these were all individual compounds, he demonstrated that it was possible to make a chemical change in various fats, producing new compounds, without vital force. In 1828, Friedrich Wöhler produced the organic chemical urea, a constituent of urine, from the inorganic ammonium cyanate NH4CNO, in what is now called the Wöhler synthesis. Although Wöhler was always cautious about claiming that he had disproved the theory of vital force, this event has often been thought of as a turning point. In 1856, William Henry Perkin, while trying to manufacture quinine, accidentally manufactured the organic dye now known as Perkins mauve. Through its great financial success, this discovery greatly increased interest in organic chemistry. The crucial breakthrough for organic chemistry was the concept of chemical structure, developed independently and simultaneously by Friedrich August Kekulé and Archibald Scott Cooper in 1858. Both men suggested that tetravalent carbon atoms could link to each other to form a carbon lattice, and that the detailed patterns of atomic bonding could be discerned by skillful interpretations of appropriate chemical reactions. The pharmaceutical industry began in the last decade of the 19th century when the manufacturing of acetyl-salicylic acid, more commonly referred to as aspirin, in Germany was started by Bayer. The first time a drug was systematically improved was with asphenamine, though numerous derivatives of the dangerous toxic atoxyl were examined by Paul Ehrlich and his group. The compound with best effectiveness and toxicity characteristics was selected for production. Early examples of organic reactions and applications were often serendipitous. The latter half of the 19th century, however, witnessed systematic studies of organic compounds. Illustrative is the development of synthetic indigo. The production of indigo from plant sources dropped from 19,000 tons in 1897 to 1,000 tons by 1914 thanks to the synthetic methods developed by Adolf von Beyer. In 2002, 17,000 tons of synthetic indigo were produced from petrochemicals. In the early part of the 20th century, polymers and enzymes were shown to be large organic molecules, and petroleum was shown to be of biological origin. The multiple-step synthesis of complex organic compounds is called total synthesis. Total synthesis of complex natural compounds increased in complexity to glucose and terpineol. For example, cholesterol-related compounds have opened ways to synthesize complex human hormones and their modified derivatives. Since the start of the 20th century, complexity of total syntheses has been increased to include molecules of high complexity such as lysergic acid and vitamin B12. The development of organic chemistry benefited from the discovery of petroleum and the development of the petrochemical industry. The conversion of individual compounds obtained from petroleum into different compound types by various chemical processes led to the birth of the petrochemical industry, which successfully manufactured artificial rubbers, various organic adhesives, property-modifying petroleum additives, and plastics. The majority of chemical compounds occurring in biological organisms are in fact carbon compounds. So the association between organic chemistry and biochemistry is so close that biochemistry might be regarded as in essence a branch of organic chemistry. Although the history of biochemistry might be taken to span some 4 centuries, fundamental understanding of the field only began to develop in the late 19th century, and the actual term biochemistry was coined around the start of the 20th century. Research in the field increased throughout the 20th century, without any indication of slackening in the rate of increase, as may be verified by inspection of abstraction and indexing services such as BIOSIS previews and biological abstracts, which began in the 1920s as a single annual volume, but has grown so drastically that by the end of the 20th century it was only available to the everyday user as an online electronic database. Characterization. Since organic compounds often exist as mixtures, a variety of techniques have also been developed to assess purity, especially important being chromatography techniques such as HPLC and gas chromatography. Traditional methods of separation include distillation, crystallization, and solvent extraction. Organic compounds were traditionally characterized by a variety of chemical tests, called wet methods, but such tests have been largely displaced by spectroscopic or other computer-intensive methods of analysis. Listed in approximate order of utility, the chief analytical methods are: nuclear magnetic resonance spectroscopy is the most commonly used technique, often permitting complete assignment of atom connectivity and even stereochemistry using correlation spectroscopy. The principal constituent atoms of organic chemistry, hydrogen and carbon, exist naturally with NMR-responsive isotopes, respectively 1H and 13C. Elemental analysis. a destructive method used to determine the elemental composition of a molecule. See also mass spectrometry, below. Mass spectrometry indicates the molecular weight of a compound and, from the fragmentation patterns, its structure. High-resolution mass spectrometry can usually identify the exact formula of a compound and is used in lieu of elemental analysis. In former times, mass spectrometry was restricted to neutral molecules exhibiting some volatility, but advanced ionization techniques allow one to obtain the mass spec of virtually any organic compound. Crystallography is an unambiguous method for determining molecular geometry, the proviso being that single crystals of the material must be available, and the crystal must be representative of the sample. Highly automated software allows a structure to be determined within hours of obtaining a suitable crystal. Traditional spectroscopic methods such as infrared spectroscopy, optical rotation, UV-Vis spectroscopy provide relatively non-specific structural information but remain in use for specific classes of compounds. Traditionally, refractive index and density were also important for substance identification. Properties. Physical properties of organic compounds typically of interest include both quantitative and qualitative features. Quantitative information includes melting point, boiling point, and index of refraction. Qualitative properties include odor, consistency, solubility, and color. Melting and boiling properties. Organic compounds typically melt and many boil. In contrast, while inorganic materials generally can be melted, many do not boil, tending instead to degrade. In earlier times, the melting point and boiling point provided crucial information on the purity and identity of organic compounds. The melting and boiling points correlate with the polarity of the molecules and the molecular weight. Some organic compounds, especially symmetrical ones, sublime, that is, they evaporate without melting. A well-known example of a sublimable organic compound is para-dichlorobenzene, the odoriferous constituent of modern mothballs. Organic compounds are usually not very stable at temperatures above 300 degrees Celsius, although some exceptions exist. Solubility. Neutral organic compounds tend to be hydrophobic, that is, they are less soluble in water than in organic solvents. Exceptions include organic compounds that contain ionizable groups as well as low molecular weight alcohols, amines, and carboxylic acids where hydrogen bonding occurs. Organic compounds tend to dissolve in organic solvents. Solvents can be either pure substances like ether or ethyl alcohol, or mixtures, such as the paraffinic solvents such as the various petroleum ethers and white spirits, or the range of pure or mixed aromatic solvents obtained from petroleum or tar fractions by physical separation or by chemical conversion. Solubility in the different solvents depends upon the solvent type and on the functional groups if present. Solid-state properties. Various specialized properties of molecular crystals and organic polymers with conjugated systems are of interest depending on applications, e.g., thermomechanical and electromechanical such as piezoelectricity, electrical conductivity, and electro-optical properties. For historical reasons, such properties are mainly the subjects of the areas of polymer science and materials science. Nomenclature. The names of organic compounds are either systematic, following logically from a set of rules, or non-systematic, following various traditions. Systematic nomenclature is stipulated by specifications from IUPAC. Systematic nomenclature starts with the name for a parent structure within the molecule of interest. This parent name is then modified by prefixes, suffixes, and numbers to unambiguously convey the structure. Given that millions of organic compounds are known, rigorous use of systematic names can be cumbersome. Thus, IUPAC recommendations are more closely followed for simple compounds, but not complex molecules. To use the systematic naming, one must know the structures and names of the parent structures. Parent structures include unsubstituted hydrocarbons, heterocycles, and monofunctionalized derivatives thereof. Non-systematic nomenclature is simpler and unambiguous, at least to organic chemists. Non-systematic names do not indicate the structure of the compound. They are common for complex molecules, which includes most natural products. Thus, the informally named lysergic acid diethylamide is systematically named N,N-diethyl-7-methyl-4,6,8,9-hexahydroindolo 4,3-FG-QUINOLE9-carboxamide. With the increased use of computing, other naming methods have evolved that are intended to be interpreted by machines. Two popular formats are SMILES and INCHI. Structural drawings. Organic molecules are described more commonly by drawings or structural formulas, combinations of drawings and chemical symbols. The line-angle formula is simple and unambiguous. In this system, the endpoints and intersections of each line represent one carbon and hydrogen atoms can either be notated explicitly or assumed to be present as implied by tetravalent carbon. The depiction of organic compounds with drawings is greatly simplified by the fact that carbon in almost all organic compounds has 4 bonds, nitrogen 3, oxygen 2, and hydrogen 1.